What happens when you throw a state-of-the-art large language model at a low-resource language like Kupang Malay? It usually falls apart. The model, trained overwhelmingly on English and a handful of high-resource languages, simply doesn't have the linguistic priors to handle the subtle lexical, semantic, and phonetic nuances of underrepresented tongues. But what if you could bridge that gap without collecting millions of parallel sentences? Today, we're breaking down a new approach called Lius, which combines instructional linguistics with a training paradigm called Continual Instruction Tuning to dramatically boost machine translation for low-resource languages. Let's set the stage. Traditional neural machine translation relies heavily on massive parallel corpora. We're talking millions of sentence pairs. For languages like English or French, that's straightforward. For Indonesia's 700-plus local languages, not so much. Take Kupang Malay, a Malay-based Creole spoken by over 5 million people in East Nusa Tenggara. It lacks substantial parallel data in major datasets like Opus or CC Matrix. Collecting it is expensive, time-consuming, and hampered by dialectal variation and inconsistent orthography. Even with the rise of LLMs that can perform zero-shot translation, performance still degrades sharply on non-English languages because of pre-training bias. The models miss fine-grained lexical mappings and struggle to capture complex linguistic phenomena. The researchers behind Lius decided to stop treating translation as a black box sequence-to-sequence task and started explicitly injecting linguistic knowledge into the training loop. They call it instructional linguistics. Instead of just feeding the model raw source target pairs, they designed 4 distinct instruction types that force the model to learn from explicit lexical and semantic features. Let's walk through how each one works technically. First, context-based prompts. The system uses KeyBERT paired with an Indonesian BART model to extract a semantic representation of the input sentence. It identifies the most semantically relevant word, looks it up in a bilingual dictionary to retrieve the Kupang Malay equivalent, and then fetches example sentences from the dictionary that contain that target word. This gives the model contextual grounding before it even attempts generation. Second, semantic mapping. Here, they take that salient word, convert it to a FastText embedding trained on monolingual Kupang Malay text, and search for its nearest neighbors in the target language based on cosine similarity. Those neighbors are then mapped back to Indonesian using the dictionary. It's a clever way to build cross-lingual lexical bridges without relying on parallel data, effectively teaching the model vector space alignment between languages. Third, phonetic-based instructions. Since Kupang Malay and Indonesian share phonological roots, the model applies phonetic rules extracted from the dictionary to map source characters to target characters. They use a sequence matching algorithm to calculate a similarity score between the phonetic representations. If the score crosses a threshold of 0.7, the words are flagged as phonetically similar. This helps the model handle morphological shifts, vowel reductions, and loanwords that standard character-level models often miss. Fourth, list group label prompts. This one groups related vocabulary using FastText embeddings and assigns categorical labels. It's essentially teaching the model taxonomic and semantic relationships, enriching its understanding of cross-lingual context, and reducing lexical ambiguity during generation. But designing prompts is only half the battle. How do you actually train on them? Standard fine-tuning usually pairs one input with one target and moves on. Lius introduces Continual Instruction Tuning, or CIT. In CIT, every single training instance is paired with all 4 instruction types sequentially. The model fine-tunes on the input with a context prompt, then the exact same input with the semantic prompt, then phonetic, then list group label, all pointing to the exact same translation target. This iterative, multi-perspective exposure forces the model to internalize different linguistic dimensions of the same sentence. To prevent catastrophic forgetting across these sequential steps, they integrate experience replay, keeping a small buffer of original training samples to stabilize the weight updates and maintain baseline performance. For the backbone, they use Cendol MT5, an open multilingual model supporting Indonesian and 18 local languages. They test 3 scales, 350 million, 580 million, and 1.2 billion parameters. Training runs on a single 40 GB A100 GPU using BF16 precision, gradient checkpointing, and gradient accumulation over 2 steps. The dataset combines roughly 66,000 Indonesian to Kupang Malay parallel sentences with monolingual Kupang Malay text for the FastText embeddings. The results are striking. Across Saker BLEU, CHRF++, TER, and Rugel, the Lius models outperform standard instruction tune baselines by 4 to 6 points. But the real story comes when you compare it to established multilingual models. Against Google's MATLAB, NMT models and regional LLMs like BLOOMZ and MT0, Lius pulls ahead by 10 to 13 points. Even in zero-shot and few-shot settings, Lius maintains a massive lead. The largest model hits a Saker BLEU of 13.27 and a CHRF++ of 32.8, which is remarkably high for a language with this level of data scarcity. They also analyzed copy behavior, which is a common failure mode where models just paste source tokens into the output instead of translating. As model capacity increases, copy accuracy drops from 23.6% down to 20%, showing that larger models actually learn to translate rather than memorize. The model also generalizes surprisingly well to unseen languages like Javanese and Sundanese, and retains multitasking ability for sentiment analysis and question answering. Under robustness tests with typographical errors, word deletions, and shuffled syntax, Lius reconstructs contextually appropriate translations with minimal performance degradation. Of course, metrics only tell part of the story. Human evaluation by native Kupang Malay speakers rated the translations on fluency and adequacy. Scores generally fell in the 3 to 4 range out of 4, indicating solid practical utility. However, interannotator agreement was only slightly above chance, with weighted kappa coefficients around 0.2. The researchers attribute this to the lack of a standardized orthographic or grammatical guideline for Kupang Malay itself, which naturally leads to divergent speaker preferences. It's a critical reminder that for low-resource languages, linguistic standardization is just as important as model architecture. Lius proves that you don't need billions of parallel sentences to make low-resource translation viable. By explicitly injecting linguistic structure through instructional linguistics and iterating over multiple instructional perspectives via continual instruction tuning, you can teach LLMs to respect the lexical, semantic, and phonetic realities of underrepresented languages. This approach is highly reproducible, computationally efficient, and directly applicable to the hundreds of languages still left behind by mainstream AI. If you're working on low-resource NLP, multilingual alignment, or instruction tuning, this paper is absolutely worth a deep read. The code and model weights are available, so go experiment with it. Let me know in the comments how you think this instruction-driven paradigm could scale to other language families. Thanks for watching, and I'll see you in the next one.